Okay, so next is an example to kind of understand how to put this in the problems. And this problem is also a little bit different because it doesn't give you the masses, instead it gives you the density. So let's read it first. So determine the center of mass for the parts shown below, and the part has a density of 3000 kilogram per meters cube and is 0.5 meters thick into the page. So there's also z direction, and that is not shown. It's just we are looking at the xy plane from the top view, okay? But we have to also remember that number. So what is given? An L-shaped part, and we are trying to find the center of mass of the location. And here's the figure. So this is what we are given for now. And what do we assume? We assume it's homogeneous material. That means the density everywhere is the same. And the plan is to split, again, as we made kind of a strategy, split the parts into basic shapes, convert into point masses, and use center of mass equations to figure out the overall center of mass. And on this problem, we also need to use the definition of density. So we are going to talk about that first in the solution. What would you estimate? So when I estimate, I'm thinking about if this was a square, so if it was a complete square like that, the center of mass will be right at the center of the square, right? But we are taking this part out, kind of, right? So that is going to be cause a shift in the center of mass. And since that part is taken out, mass is more on this side. So this center of mass is going to shift there. So I expect this new center of mass to be not at the center of the square, entire square, but a little bit on the lower right corner, that little square. Okay, on that little square. Again, this center point would be 1 meter by 1 meter. So less than 1 meters would be a good estimate, or you can be more specific and say maybe it's 0.8 on each. And for the z-axis, these are x and y axes. And for the z-axis, since the thickness was 0.5 meters, it's going to be half geometrically. And that's going to be at the 0.25 meters. So we don't really need to solve for z because it's already known. It has the same thickness, so it won't change the answer, okay? But we need to figure out x and y thicknesses, or sorry, center of mass. Let me get rid of some of the things I've shown here. And so the step one, again, we are going to break into simple shapes, and we show that on this figure. So we are splitting into two pieces, one rectangle, another square. You can do 3 little squares, or make the rectangles horizontal instead of vertical one. It's really up to you. It doesn't matter, it won't change your answer. You can even give it a try just to see that it doesn't make any difference. So once you break it into simple shapes, and you are going to note that where the center of masses are, and now find the mass of that center of mass for each piece. Okay, so we're saying that for part 1, the rectangle here, it is right at the center. Again, I hope that this is clear because you just do diagonals and find that center point. I didn't draw it very nicely, but find that diagonal point, and that diagonal point, see what is x1 and y1, okay? And x1 here is going to be, so since this point here is 1 meters, x1 is half of that, so it's going to be 0.5, so it's really easy to find that value. And since this is 2 meters, you can see that there are two 1 meters here, and y1 is going to be half the way, so it's going to be simply 1 meters. Okay, so x1 is 0.5 meters, y1 is 1 meters. You do the same thing for 2, again diagonal, and find what x2 is, but realize that you're measuring this from here, so this is our origin point, okay? What is x2? So if you look at that piece 2 first, that is 1 by 1 square, right? And that means the x2 is going to be halfway, so it's going to be 0.5. But there was already, it starts from 1 meter, so x2 is going to be at 1.5 meters. we're adding 0.5 to 1. And y2 is going to be right here, since it starts from 0, and it's half the length of y value, which is 1 meters, and then you're going to get half of that, which is 0.5. Okay, I hope those values are clear. So what we would do is, again, use the equations and now find out m1 x1 plus m2 x2 and divide by total m. However, we don't know the mass, so that's adds an extra step to this problem, which is different than what we looked at it in the text. So we need to understand how to use this density equation. Okay, so the density is, as you can see, kilogram per meters cube. So density is usually shown with rho is mass divided by volume. Okay, because it's kilograms per meters cube. And in here, the density is given. So we are going to make use of that to figure out what the mass is. So what is M1, for example? M1 is going to be rho times V1. What is V1? It is the side. So if that was a rectangle, and I just want to give you an example, it's A times B times C, all the sides multiplied, right? And if it was a square, it would be then A times B times C again, but all those A's, B's, and C's would be the same, so that it would just maybe A cube or something. Okay, so using this definition, we are going to get the masses. And rho is the density. Again, this is our rho here. 3,000 kilogram per meters cube. A, B, C are kind of, I'm saying that those are the side lengths. You can think of maybe X, Y, and Z. Okay. Here what we have for the rectangle, the first one, 2 meters, is the Y, the kind of the height for the first piece. And times 1 meters, so I'm kind of focusing on here, this is the volume. Okay, or you can call it V1. So we're multiplying all the lengths. It's 2 by 1 on this plane, but there's also thickness, which is 0.5, and we are adding that too. And when you multiply all these three, you get meters cube, right? And meters cubes are going to go away. You're going to end up with kilogram. And in this case, again, because of the cancellation between these two, and this is only 1, you're going to get 3,000 kilograms. And the location of the center of mass, as we already found out, is at 0.5 and 1. Always X first, Y later, and if you have Z, Z comes next. Always in that order. And M2 is again density times the volume. So this part is V2, okay? And what is that? It is 1 by 1 times 0.5. That's the thickness. So we are multiplying all these things. And that is giving us half of the mass as we got from M1, as it should be, because again, geometrically, these are homogeneous material. You can see that piece 2 is half of piece 1. So the mass-wise, it should be also half if it is homogeneous. And it is. That's the assumption we made. And again, taking note of the locations. So this was X1, Y1, and this is X2, Y2, because these are the ones that we need in this equation here. I want to go back and show you again. This is the equation that we will apply, and we need those numbers. We need mass and X and Y, so that's what we gathered so far. And all we need is to kind of put these together now. So since we have only 2 pieces, our equation looks a little bit simplified, because we have only 2 terms added. And it really helps if you kind of draw a table to show these. So we are just writing how many parts we have, especially if you have more than 2 parts, it will help you a lot more. Maybe this is too straightforward, but let's discuss this here so you can practice this in the coming problems as well. So that's MI is how many masses you have, how many pieces you split. We have 2, right? And the first one we found out as 3,000 and second one is 1,500 kilograms, and we are putting them. And at the bottom, we are writing what the total mass is, right? This is the total mass. So you're just simply adding them up. And next we have xi and yi. If we have also z component, we could also write it. Since z is not changing, we are not showing it here, but we already know that z is 0.25 meters, okay? And let's write down what the initial the x values are. What is x1, what is x2? Again, they're coming from here. These are the x values, 0, 5 and 1.5, and these are the y values. They're going right there, 1 and 0.5. And here for the center of mass equation, since we need to multiply mass and the position, and we need to do that consistently. So we are doing for the first one is m1 x1, so it's 3,000 kilograms times 0.5 meters, and this is what we're getting. Check the unit. Since it is mass times position, it's kilogram meters. Same thing, multiply these two, you're gonna get this. And again, multiply m and y, you're gonna get the first one m1 y1, and this is m2 y2. And once you get all of these, you're simply adding those up, these two to get that, and these two to get this, okay? And that's the sum. At this point, all you need to do is take those sums and divide by total mass, as we show here, to solve for x or y component of the center of mass. So again, it was less than 1 meters each, and it was close to 0.8, but it is, to be more accurate, it is 0.83 meters on each. And if you remember, we also said that the z center of mass, since it is the same for all, it is half of the 0.5, the thickness, which is 0.25 meters. Okay, you could also add this in here. So our answer agrees with our estimate. For many objects, we can quickly get an intuitive sense of where the center of mass is, because it's the same as geometrical center if they are homogeneous. And again, unless otherwise as stated, we will assume they are homogeneous. And for this problem in the z direction, the center of mass would be located halfway through the part, as we shown here, 0.25 meters. And if this object was thrown, the center of mass would follow a parabola, and the center of mass motion characteristics could be predicted using projectile motion equations. So there's nothing new after that. You just need to find those points. This is the reason we're adding these steps, okay? So what we are discussing right now is usually initial step of a new problem, but the rest is going to be what we did in the previous chapters. So it's a little bit more sophisticated and more complex because we are now adding an extra step to the problems. So as with other problems, we illustrate a systematic approach for problems requiring calculations of the center of mass.